Hi, everybody. I'm here to give the presentation for our project one for week three. I represent the group of Austin, myself, Chester, Deepak, and Michael. So the data set that we chose to go with was from the Stanford data sets, and it's a data set of Facebook relationships. So we have over 4,000 nodes, each representing a person, and we have 90,000 edges representing their friendships with other people. So what we wanted to do was we wanted to, start with this data, grab it, import it, and build out a network, and build out the attributes for that network, and then test one of those attributes, which is gender, and see if there's a difference in the mean and median for some of the centrality scores. All the data is anonymized, so that means that we kind of just have numerical values representing things like gender. So we can't really distinguish what they are. But in the case of gender, there's two numbers. So we'll just eventually look at it by assuming one means male and one means female. So the general workflow is that we're going to display our files so you can see what we're looking at. We got to figure out how to join them. There's over 20 files. Then we want to build a dictionary to store the attributes. Then we want to build out the networked nodes and edges. We want to build out centrality scores. And then we want to create separate male and female data frames and run t-tests on those centrality scores. And then at the end, we're going to do a little visual display of the networks by gender and by location. So we wrote in our libraries, and first step, reading the data. Okay, so for data that was supposed to be clean data, this was difficult. It came as a tar file with something like over 30 different files. But really what we needed were 20 files, of which 10, I think, were called the .feat files, and 10 other ones were called the .feature name files. There's also a Facebook CSV file, which conveniently was stored correctly and had all of the edges for our data set. But the attributes were scattered throughout 20 different data frames. So what it kind of looks like is if you look at these .feature files, we have all these zeros and ones mapped, and these are our attributes. And then the .feature names are the rows represent the attributes. So if you look at the shape, essentially, it's reversed. So all of these names technically belong in these columns, except for column 0. That's why 225 versus 24, because this is actually just our nodes and the numbers for our nodes. So what we needed to do first was figure out a way to combine these two files together to insert these names into here, and then figure out a way to take these 10 separate files that we'll now have with correct names and figure out a way to join them together. So here we are. What we first do is we just create some list comprehensions to create these file names because I think it was just like a couple of random integers in front of a file name. And so, 0.feature name, 0.features. So we load all these things in. What we do then is we create an empty list, and we search through and we try and do that flipping of the column names. And that's essentially what's happening here is we are joining the .feature with the .feature name together by grabbing these row features and inserting them into the column names. And in the end, what we would have here is, being that there are 10 different files, or possibly 9 different files, being that there are 10 different files, we're left with 10 different data frames in one big list. And at the end here, I just did a type check just so you can see it, that these are all different individualized data frames. So from here, where do we go? Well, we decided that we'd build out a dictionary for the nodes. So what's done here is we're just setting up a blank dictionary, and for that dictionary, the index value is going to be the node, and the key is going to be an empty list. And then what we tell it is that we say, okay, look through all these data frames, and whenever you come up to a node, I want you to append to the list the attribute. And essentially, what we get from that is we get, imagine this is a node, so this is our node 10, and it's gone through all the data frames, and it has all of the attributes mapped with their values. From here, we had to, this is our first building out our network. So the first part of this is pretty simple. The Facebook combined text has our edges, we load them in. Then what we had to do was we realized that we didn't need all of these values, but we realized that these are hot encoded, and what we need to do is extract the whichever feature had the 1, we had to extract it, and we realized what we could then do is we could take that integer, so I say feature 14, and we could just do it as education value 14. Which will reduce greatly the amount of information in the data set. So instead of having all these hot encoded birthday anonymized features, which there could be up to 100 of, there's just one birthday anonymized with one value representing whatever feature it was. So that was done here, and we actually just show a basic graph of it. This is showing you what the attributes look like now in our node. You can see it looks fine, perfect. From here, we built out centrality scores. The eigenvector centrality takes a long time to build. And what we did was we created individual data frames per centrality score, and that data frame consisted of the nodes and the centrality score. And then we just joined them together or merged them together all on the nodes. And this is what we're at now with our data frame. From here, we realized, okay, well, now we need to do the same thing that we did above for the dictionary for our data frame. And you can see that we extract all those birthday columns into the word birthday, all the education classes. And now we have just the column names. From here, we had to do this to now grab the dictionary values and insert them into these values here. Thus, as you can see, we build out our data frame, and for birthday, instead of having all that uncoded, we have the value 7 for node 3. At this point, a lot of the hard work is out of the way. It's kind of incredible that for a data set that was supposed to be clean, that's the way they stored their data. But here we are, and now we're like, okay, let's see if gender makes a difference. So for the purpose of the study, we just assumed that males were 77 and females were 78. And we just split our data frame because it's easier to work with. And this is what we get, right? We can see a description of the males. We can see that there's significantly less males than there are females, right? There's 2,400 on this one and 1,500 in that one. There's all kinds of differences. We thought that maybe a good way to look at it would be to just, if we want to see differences in the mean, let's just subtract these things and see what we get, right? But in and of itself, while we can see there's some difference, it's relative. So we need to run a t-test, and that's what we do below. So we run a t-test on all 3 centrality scores with the null assumption that the male and female populations are in fact the same. And it turns out that for degree centrality, it's extremely close to being significant. For between centrality, it's also extremely close to being significant. And for eigenvector centrality, there's a clear significance showing that these means are in fact not the same. But after that, we thought, okay, well, means aren't robust to outliers, right? So perhaps there's someone in the data set that is influencing this. So why don't we look at the median values? And there was actually a cool function that stats.median test, and what it does is it sort of creates a population median from different samples, and it compares those samples to that median to tell you if those samples in fact are statistically different from that population median. In this case, what we actually found was that degree centrality and eigenvector centrality were actually not significant in showing a difference, but between centrality actually showed a difference. So from here, we decided that okay, well let's graph our network and see what it looks like. It unfortunately this is on a laptop and it's more difficult to see. But what I did was I sorted a data frame below here to look at between centrality because I figured if there's anything we're going to be able to tell on this thing, we could probably tell a node that's kind of connecting a lot of things. And there were several more that were visible before, but at the moment we see like node 136. So we'd assume 136 is connecting all these different groups. So perhaps it is important in terms of between centrality. And in terms of between centrality, it actually shows up as out of 4,000 nodes, about the 19th highest between centrality in our network. Some of the other ones are probably captured somewhere in this, but nonetheless, it's a cool thing to look at. From here, we thought, well, being that we looked at gender, why don't we map out gender? You're not really going to be able to tell much from gender. For one, there's significantly more of the yellow than the red, or females than males, but it just can give you a general idea. And then But something that we thought would show difference is location data. So we kind of assumed that anybody on Facebook that you're friends with, it has a high likelihood of living in closer proximity to you. So what I did was grabbed the top 9 locations which occurred most frequently, and we color coded each of them. So we're thinking that of these 162, will these dots show up next to each other? And what happens is, in fact, they do. So we can see that clusters form in multiple areas based on location. So we can see blues are clustering together, orange is clustering together, the reds are clustering together, the yellows are clustering together here, purples are clustering together, um, brown or whatever color this was is clustering together. The rest of the nodes were colored in black, so there could be more relations, but it's pretty clear here that location is extremely significant in determining how close you are to somebody in the network, or the amount of relationships you have with that person. And that was our project.